Have you ever noticed how even the smartest AI models today are kind of stuck in the past? They get all this training and then that's it. They're frozen. They can't actually learn from the conversation you're having with them. Well, we're going to break down a really cool new paper today that might just be the key to changing that, letting AI learn on the fly. Let's get into it. So here's how we're going to tackle this. First, we'll talk about the core problem, why AI has this static memory issue. Then, we'll look at an older idea to fix it and see where it fell short. After that, it's all about the new breakthrough, what it is, how it works under the hood, and, of course, the results. Finally, we'll zoom out and think about what this means for the future. All right, first up, let's really dig into the heart of the problem here, this train then deploy limitation. I mean, it's a fair question, right? We've got these incredible models that can write code, whip up poetry, you name it. But the second you ask them to learn something from a long document they're reading right now, they just can't. They hit a wall. So what's going on there? It all comes down to this idea of train, then deploy. You can think of it like this. The AI spends a ton of time in this massive training phase, like a student cramming in a library for months. But the moment it's deployed out into the world, the library doors are locked forever. All its core knowledge, its weights, are totally frozen. This makes it really bad at handling tasks that evolve over time or learning from the stream of information we see every day. Now, of course, researchers have been trying to crack this nut for a while. So let's look at one of the first big ideas, something called test time training, or TTT, and see why it wasn't the perfect solution, especially for these massive new language models. On paper, the idea behind TTT is awesome. You give the model a small set of fast weights. Just think of it like a little mental scratch pad. As the model sees new data out in the real world, it can jot down notes on this scratch pad, updating it to adopt to whatever it's looking at. It's a way for the model to learn while it's working. Sounds great, right? Well, when the rubber hit the road, it ran into three huge problems. First, it just wasn't compatible. You couldn't just add it to a model you already had. You had to add new parts and do a costly retraining from scratch. Second, it was painfully slow. Updating after every single word is just not how modern GPUs work. They want to do things in parallel, not one by one. And third, and this is maybe the biggest deal, its goal was just wrong. It was learning the wrong thing. And that is where this new research comes in. It's a framework called in-place test time training. And it's so elegant because it was designed from the ground up to solve all three of those problems. Okay, so remember that architecture problem? Instead of bolting on some clunky new component, this method does something way smarter. It looks inside the model, finds an existing part, this final projection matrix in the MLP block, and just repurposes it as its fast weights. It's brilliant. No new layers, no retraining. You can literally just drop it into an existing model. This diagram shows us what's happening. On the left, you've got your standard transformer block. But the magic is in that MLP block. It's doing this little two-step dance. As the data comes in, it first applies its current knowledge to process it. Then, right away, it updates its knowledge based on what it just saw. It's this tiny, continuous learning loop happening right inside the model. So, what about that speed issue? Well, instead of that slow, one-word-at-a-time process, this approach works on big chunks of text, like 512 or 1,024 words all at once. This lets it take full advantage of modern hardware, making the whole learning process fast and efficient. And finally, we get to the learning goal, which might be the most important fix. The old way was about reconstruction. It was basically trying to memorize the word it had just seen. This new method changes the goal to prediction. It uses the current word to get better at predicting the next word. This aligns the learning process perfectly with what a language model is actually supposed to do: figure out what comes next. Okay, so let's pop the hood and get a little more technical. This whole thing really boils down to two key innovations: that smarter learning goal we just mentioned, and a super high-speed algorithm that makes those chunky updates actually work. This really breaks down that change in thinking. On the left, the old way is just trying to associate a key with a value from the exact same token. It's looking backwards, basically just memorizing what it saw. But on the right, the new LM-aligned way forces the model to associate the key from this token with a value from the next token. It's always looking ahead. And the math here is simple but powerful. By focusing on the next token, the update is directly helping the model get better at its primary job: prediction. And hey, don't just take my word for it. The paper actually proves it mathematically. Theorem 1 basically says this new LM-aligned goal is guaranteed to make the model better at guessing the next word. The old reconstruction method, it offers zero predictive benefit. So it's not just a hunch, the math says this new way is just better. So, how do you update in big parallel chunks without breaking the step-by-step logic of language? This is where a super clever algorithm called a parallel scan comes in. First, it calculates all the little weight updates for every chunk at the same time. Then, and this is the wild part, it uses something called a prefix sum to instantly figure out the cumulative history for every single chunk. It makes sure that chunk 5 has learned from 1, 2, 3, and 4, but it does it all at once, not in a slow loop. Finally, it applies the correct historically aware weights to all the chunks. You get sequential logic, but at parallel speeds. It's the best of both worlds. So the theory is really elegant. The algorithm is super clever. But you know what really matters? Does it actually work? Let's look at the results. All right, these charts show something called perplexity. All you need to know is that it's like a golf score for language models. The lower the number, the better. And just look at that dark blue line. That's our in-place TT. In both models, it is consistently outperforming everything else. The longer the text gets, the bigger its lead becomes. That's a crystal clear sign it's doing a better job learning from context. Now, this is really cool. Remember we talked about processing in chunks to be faster? This chart basically asks, well, what's the perfect chunk size? And you can see there's a clear sweet spot, a Goldilocks zone, right around 512 or 1024. This is awesome proof that the whole chunk-wise idea works. You get the speed without sacrificing any performance. For me, this table is the real kicker. The researchers took a popular existing model and just dropped in their new method. No retraining, just plug and play. And look at the results. The performance gets a significant boost, especially when the context gets really long. At 64,000 tokens, the score jumps by more than 4 points. That's a huge real-world improvement. Okay, so let's take a step back and talk about the big picture. Why does any of this really matter? At the end of the day, in-place TTT is so much more than just a performance hack. It feels like a really important step towards a new kind of AI. An AI that can learn continuously from its experiences, kind of like we do. We're moving away from these static, frozen-in-time models towards something more dynamic, something that can adapt to the world in real time. And that leaves us with a really exciting question to think about. What happens when our AI tools are no longer just repositories of old information, but can actively learn from the document you're writing or the data you're analyzing right now? What new things could you create when your AI can learn and evolve right alongside you? The possibilities are pretty incredible to think about.